Mm-hmm.
Hello everyone, I hope you're doing well. In this video, we'll see that how we can find out the Miller indices of planes in cubic unit cell. Okay, so I know that you don't like the long intro, so let's quickly get started and see the steps that are involved, and then we can have some examples. Here we can see the steps that are involved in finding out the Miller indices of the plane. The first step, the most important, is to define the coordinate system. And while defining the coordinate system, you have to make sure that the origin is not part of the plane, or you have to select the origin such that the plane doesn't pass through the origin. We'll have that example in the future. You'll see that what happens when we have that. For example, we can see this case. Okay, in that case, the predefined coordinate system, okay, is here, and these planes doesn't pass through the region. However, if we consider this example, we can see that the plane and the origin, the predefined origin, obviously they both intersect each other, so we should shift our origin such that the plane doesn't pass through the region. Okay, this is the requirement, and we'll see that how we can fix that. And whenever that happens, it will be completely apparent to you, as you saw in that previous example. So the first step, the most important, is to define the coordinate system and acknowledge the axis lines that you have. Okay, because intercepts are something that are relevant to axis lines. You should know where does the axis lines lie, because that is how you are gonna determine the intercepts. Well, now when you have defined your coordinate system, and now you know where is the x-axis, y-axis and z-axis, you know all of that, the second step is to find out the intercepts that the plane is making with these axis lines. Okay, in case of planes, keep that in mind that these axis lines plays a vital role. You should know where does they actually lie, because the point where the plane cuts those axis lines is actually intercept. This is what intercept means. So we'll see that why it is very important, like why the axis lines are really important, and we'll also understand how we can find out the intercepts. And we should keep that in mind, that in case of planes, intercepts are the central thing and the tricky thing that needs to be determined. Rest of everything is really simple and straightforward. However, finding out the intercepts is a tricky part, so we should learn and understand that how we can do it efficiently in any case. Okay, next, the next step is to take reciprocal of each intercept, and we'll take inverse of each of these intercepts. We'll remove any fractions if we have any, and then we'll include those numbers that are those integers in circular brackets, and that is how we'll get our Miller indices. Okay, it could be confusing at first, but once we will practice it, it will become crystal clear to you people. So let's get started with first example. As we can see here, we have two planes inside a cubic unit cell. The first is plane A, and you can see this is the plane A. All right, you can see these are the boundaries of plane A. This is in dark orange color, while the plane B is in light orange color, and it has a different shape. So first we'll be dealing with plane A, and then we can deal with the plane B and so on. All right, so here first of all we need to define our coordinate system. And when we are dealing with axis lines, the selection of origin plays a major role, because it can complicate or facilitate the process of finding the intercepts. We have to select a point cleverly such that the plane is cutting those axis lines in most of the points. Okay, so for example, if I take this point as origin, okay, I can take it, that is totally fine, but we have to select we have to select the coordinate system or origin that makes our process of finding the indices really easier. So let's see that how we can do that. If I take this point as origin, so this is the x-axis that way, and this is the y-axis, and vertically upward will be the z-axis, and you can see that the plane cuts the x-axis at this point. Okay, obviously, apparently you can see that the plane is cutting the x-axis. This pink line is x-axis, and the point where this blue plane cuts this pink line is this point. Okay, as we have seen, and this point is taken as 1, as we know that from one corner to the other corner of the unit cell, the length is taken as 1. Okay, we'll have other parameters like half and 1/3 as well. We'll see that later, but for now we know that from one corner to the other corner, like from this corner to this corner, the length would be 1. So you can see that it's cutting at 1 point, and for y-axis you can see this pink line is y-axis, and the plane is cutting this y-axis line at this point. Okay, and for z-axis you can see that the plane is not cutting this z-axis line. This is vertically upward is z-axis line. Okay, and plane is not cutting the z-axis line at any point inside this unit cell. You can see this point is not the one. You are apparently seeing that it's cutting it, but you can see that these dotted line shows that these dotted lines are behind the plane. They are not a part of the plane. Okay, you have to be, you know, really good at reading the diagrams. You should know where does the plane is actually lying. You can see the plane is slightly it's in front of the z-axis. It's not cutting it. So if we take this point as a region, then we will have a problem with z-axis. But there's one more point that can facilitate our process. Okay, so let me show that one point to you people, and it's this point. If I take this point as origin, okay, so this backward direction would be negative x-axis, right? If it's forward, it's x-axis, positive x-axis. If it's backward, it's negative x-axis. Okay, if it's, you know, left side, it's negative y-axis. If it's right side, it's gonna be positive y-axis. So we can take it's negative y-axis, right? And then vertically upward would be the z-axis, and we can see that the plane is cutting here the z-axis at this point. The plane is cutting the y-axis at this point, and the plane is cutting the negative x-axis at this point. So this is how we have defined a suitable origin, such that this plane is cutting all of the axis lines within this unit cell, and we can easily determine the intercepts. Okay, so the selection of origin is really important. I used to use that equation method in case if we are not able to find a suitable region where we can find all of them. We'll learn that method as well, but here the selection of origin was creating, you know, less of a mess, so we can use that new origin now, and we can find intercept really easily. So if you can use the simpler method, then why not? And we'll learn different methods as well, which are, you know, whose applicability is far beyond the selection of origin. You can use that method at any time, but here I want to mention this method because it's really quick and easy. So here we will be defining this as the positive the negative x-axis, right? And this is the negative y-axis. This direction is negative y-axis, right? And the vertically upward is the positive z-axis, and I'm gonna show it in dotted lines. So okay, that is positive z-axis because it's upward. Whenever we have the z-axis downward, it is negative. If it's upward, it's positive. If it's right, it's positive. If it's left, it's negative y. And if it's backward, it's negative x. If it's forward, it's positive x. Keep that in mind. All right, so we can see clearly that the plane is cutting the x-axis at this point, which is -1. Okay, because that is a region, this point is a region. So from this point, from this corner to this corner, the length is 1, and since it's negative direction, so it's gonna be -1. So we have found the x-intercept, which is -1, right? And then we have seen that this is negative y-axis, and the plane A is cutting the negative y-axis precisely at this point, which is, you know, one corner from origin, okay, to the other corner, and it's gonna be 1. Okay, and -1 because it's negative y direction. All right, and lastly we can see that this is the positive z-axis, and the plane A is cutting the positive z-axis at this point, at the corner point. Okay, so from origin we always take points in reference to origin. Okay, so intercepts are always taken in reference to origin. So we can see in reference to origin, which is taken as corner, we have the intercept to the other corner of the unit cell along z direction, so it's gonna be 1. Okay, from one corner to the other corner of the unit cell, it's gonna be 1. Okay, when it's in, when it's in the direction of these boundary lines. Okay, from one corner to the other corner along these boundary lines, we always have that length to be equals to 1. But it's not gonna be 1 when you are moving, inside these boundary lines. For example, if you take this corner to this corner, this length is not gonna be 1 because it's not across the boundary line. Only these boundary lengths from one corner to the other corner would be taken as 1. Alright, so keep that in mind. This length and also this length, it's gonna be 1, and so on. So yes, we have successfully calculated our intercepts. Now let's move to the page and proceed with the later processes because we have calculated the intercepts. Well, these are the intercepts for the plane A. We can see that this is the x-intercept, this is the y-intercept, and this is the z-intercept. Now the next step here is to take reciprocal. Taking reciprocals of each of these intercepts. So what we are going to do is that we will divide it by 1. So 1 divided by 1, 1 divided by minus 1, and 1 divided by 1. So we are left with 1, minus 1, and 1. Alright, so we can see that there are no fractions involved. If there would have been any fractions, so we were supposed to remove those fractions, but here we can see there are no fractions involved. So these are the final Miller indices for plane 1. So we can write it like, first we'll write x-intercept, then y-intercept. Since it's negative, we'll write 1 with a bar over it, which shows it's a negative number, and then 1 again, and we'll enclose it in circular brackets. Alright, so these are the indices for plane A. Now let's do it for the plane B, and for plane B we can see the case is simpler because the predefined coordinate system is working well in here. We can see this is the positive x-axis, this is the positive y-axis, and this is the vertically upward is the z-axis. Alright, so we can see here that the plane is cutting the x-axis at this point precisely, and it's cutting the y-axis line, the green line, at this point. And we can see that for z-axis we will see that there is no problem at all because we can see that these boundary lines, we can see one of the boundary lines of the plane. Okay, we can see these are the boundary lines. These are completely straight, which means that they are parallel to z-axis. Okay, if any of the boundary of the plane is parallel to any of the axis line, for example, here we can see that these two boundary lines, this one and this one boundary line, is completely parallel to the z-axis. That is why we can say that the z-axis is parallel to the plane, and two lines or two planes or anything that are parallel to each other, they never cut each other, which means that the z-intercept would be taken as infinity. Okay, so we mathematically say this situation like when two parallel lines are here, then we say that they will cut each other at infinity. So we never reach infinity and we never cut each other. That is how we deal with that. So the z-intercept would be taken as infinity. There is no problem at all. And for x and y-intercept, you can see clearly that the plane is cutting the x and y-axis at, obvious points. So let's see here that, okay, so this green line is actually the x-axis and this one is the y-axis, and vertically upward is the z-axis. And we can see where does the plane lies. Okay, you can see these are the boundaries of the plane, and okay, here and here, this pink line is actually the plane and the green line is actually the axis line. So where does this pink line cuts the green line? You can see on x-axis it's cutting here, and we can see that what does this point is. They have already shown that this point is half along x. Okay, but in case if you are confused that you don't understand these lengths, so there is one method that I always teach people and students, because that method is gonna be helping you when you will be drawing the planes inside a inside the unit cell. So it's a method that is helpful for you for different kind of problems as well, so you should learn it. And we can do that by saying that from origin, okay, what does one length would have be in x direction? So this length would have been 1, and you can see that this this point where the plane is cutting the axis line, you can see before that and after that the lengths are equal. You can see the lengths, both of these lengths, this length and this length, okay, both of these lengths are equal, which means that this point is dividing this whole length into half. All right, so when we have two equal parts before and after that cutting point, it means the point is half. Okay, and we'll see when it would be 1/3, and as here we have, so we'll have that example as well. So we can see that the plane is cutting the x-axis at half point. So half, it's gonna be the intercept for x direction, so we have half as x intercept for plane B, right? And we can see where does the plane, the pink line, cuts the y-axis. This is the y-axis, and you can see that the point where the pink line is cutting the green line is this point. Okay, and we are now maybe you are confused at what does this point corresponds to. Is it 1, 1/2, 1/3, 1/4? How we are supposed to know that? So let me show you this method from origin, always starting from origin. Okay, from this corner to this corner, this length would have been 1, right? And this is the point where you want to know that what does this point is. You can see that this length is shorter before that and this length is longer. It means it's not half. Okay, half means when the point is dividing the length into two equal parts. That is what half means. So what does this point mean? So if I make one more point like here, such that these three lines are equal to each other, you can see this length is equals to this length is equals to this length, which means that this line has been divided into three equal parts. When there are three equal parts, when we can make three equal parts out of it, it means that each part is 1/3. All right, and in reference to region, how does this numbering works? Let me show you that as well, because that is really important. So the closest one from origin will be first, like 1/3. Okay, the second one will be 2/3, since it's second, so it's 2 times 1/3, and the third one is 3/3, and 3 and 3 cancels out, so we have 1. So we already know that this point is 1. Okay, but now you know that how. Okay, if we have three partitions, so the first part will be 1/3, second part will be 2/3, and the third part will be 3/3, which is 1. Okay, so that is how the calibration works, and it always works that way. Okay, we will understand it more when we will be drawing the planes from given Miller indices, because it's gonna help you a lot when you are drawing the planes. Okay, but here you should know this as well. So this point where the plane cuts the y-axis is 1/3, so the y-intercept is positive 1/3. We can see that all of them are positive directions, and for z we have infinity as the intercept, as we can see that one of the boundary lines, okay, this is the boundary line and this is also the boundary line, they both are parallel to the z-axis, hence the z-intercept is gonna be infinity. All right, and we can also confirm it using the equation of the planes. All right, but you don't have to, you can clearly see that they are parallel to each other. All right, so let's move to the paper and see how we can proceed after that. Well, these are the intercepts for the plane B. We can see it's 1/2, 1/3 and infinity. Now the next step is to take reciprocal. All right, so we'll take reciprocal. It will be like we'll have 2 divided by 1, 3 divided by 1, and it will be 1 divided by infinity. Okay, because in division it's 1 if it's nothing. Okay, so we will invert them, invert the order, and we have 2, 3, and 1 over infinity is 0. So we can see here that there is no fraction involved. So these are the final Miller indices for the plane B. Okay, since there is no negative number, so no bars are needed, and yeah, these are the final Miller indices for plane B. Well, let's suppose that you are not confirmed that it's infinity, because sometimes students don't recognize it. Okay, they get confused. So for example, you have accurately determined 1/2 and 1/3. Now let's see that how we can use the equation of planes to confirm that the z-intercept is infinity or anything else. Like we can find out the z-intercept from equation. So this equation is really simple. It's an equation of plane where we have this x over a plus y over b plus z over c. Here a, b and c are the intercepts. Okay, a is the x-intercept, which is 1 by 2 that we found. B is the y-intercept, which is 1 by 3 that we have calculated, and C is the z-intercept that we need to calculate, and putting that all equals to 1. Here x, y and z are any points on the plane, and the selection should be such that the point that you wanna calculate shouldn't be 0. For example, we want to calculate C intercept here, which is z-intercept. Any point that we take from the plane, this xyz, shouldn't have z to be 0. If z is 0, then this whole quantity will become 0, you know. Okay, 0 over c is 0, so c will vanish, and that is not what we want, because we want to calculate c, so it should be there. So we should choose a point where at least z is not 0. Okay, so let's take a point on the plane. We can see this whole length is the plane, and we can choose this point which is on the, you know, top, and here the z is not 0, or this point. Both of them will work fine for us. So I can choose, for example, this 1 by 2 one. Okay, we can use this one. So let me clear let me clear out some of these mess, and we'll use the similar coordinate system here, because we'll stick to the coordinate system that we have chosen so far. And finding intercepts and finding the coordinates is a different thing. Okay, so starting from origin, how much we have to move in order to reach this point, which is a point on the plane that we will be using here in this equation. So starting from origin, we'll move, for example, first we'll move upward, okay, by 1 unit, because we moved from one corner to the other corner of the unit cell. So we moved 1 unit along z direction. Okay, so z point will be taken as 1. Okay, z will be 1. Now I want to reach this point, so I have to move along x direction, because this direction is actually x direction. So I'll move half unit along x to reach this point. Obviously they have also shown us that it's half, and we also know that it's half, okay, from the logic that we used before. So it's half along x. Since we don't need to move along y direction, so the y point will be taken as 0, right? So let's plug all of these values into this equation and see what does the c point is. Well, let's see this method that works in every case when you are confused in, you know, in any intercept, or when you can't determine it by looking at the figure. You can use this method. Just get a point, suitable point, such that the coordinate corresponding to that intercept shouldn't be 0. Okay, so we just made sure that z coordinate was not 0 for the point that we are taking in this equation, and we are supposed to calculate the z-intercept. So let's see that whether we are getting infinity here or not. So this is the equation of planes where x, y, z are any point on the plane. You choose it yourself, it's your choice, and a, b and c are the intercepts of the plane, and equals to 1. Now let's put these values into this equation and see what we are going to get. So x is 1 over 2 divided by a is 1 over 2 again. So y is 0, so the whole quantity will become 0. We don't need to, you know, write it. It's going to be 0 at the end. And z is 1 divided by c, that is equals to 1. So this cancels out, 1 over 2, 1 over 2 cancels out, and it's 1 plus 0 plus 1 over c, that is equals to 1. Now we can take this one to the other side. So it's going to be 1 over c equals 1 minus 1. 1 over c, that is equals to 0. And we can see it's 1 over c equals to 0. So we'll invert, we'll take reciprocal. So it's going to be c by 1, that is equals to 1 over 0. Okay. So c is equals to 1 over 0, that is equals to infinity. 1 over 0 is infinity. So we can see here that the z-intercept came out to be infinity. That is something that we predicted at first place as well, but now we are confirmed that we are, you know, sure, and we were correct. And yeah, that is the method that you can use, like even to determine x and y intercepts as well, by choosing a suitable point on the plane. Okay, this method is really a magical method, because most of the times the questions that we get in exam are tough. Okay, so we can use this equation safely by choosing an appropriate point on the plane and then finding out a, b and c one by one. You know, if you choose a point whose y and z coordinate are 0 and only x is non-zero, then you can safely determine a. Similarly, you have open power using this equation. So that is it for this video. We'll be doing more of these videos and I'll solve more examples that would be more tough. Take care, goodbye, and if you have any questions you can ask me in comment section.